My name is Nam, and today I'm going to talk about my work called Containment of Misinformation Spread. And in fact, this work has closely related to a previous talk that we just have about, so you may see some overlap. So for the introduction, online social networks, as we all know, have become more and more popular with the introduction of Facebook, Twitter, Google+, and Pinterest. People now have more short way to socialize online. So beside that good side, there comes a lot of bad thing about online social network. For example, you encounter the risk of exposing your private information. And these online social sites are also ideal place for people to inject virus or worm propagation on that. And another issue that's currently arising is the problem of misinformation or faulty information spreading on online social network. So let's take a look at the bad effect of misinformation. In late 2009, people observed that the swine flu tweets on Twitter, which are later found incorrect, has caused a wide panic in the general public. Okay? So people discuss a lot about the swine flu right here. As you can see, it's just for fun. And then another one in 2011 where Fox News channel on Twitter spread the tweet about President Obama was killed. And of course, this channel was hacked. And this tweet was just a joke. But if you look at how many people follow the channel, then it's gonna cause a really, really big problem if people believe in that tweet. Okay, so misinformation has a lot of bad effect. Oops. And then, so what are the difficulties of containing misinformation on online social networks? So the first thing is because of the huge magnitude of these social sites. Needless to say, they have millions of users and billions of connections. So if you take a naive strategy like immunization, then the question to ask is which tweets or which posts are we going to read to see whether they are bad or good? And then the next question is from whom which we're gonna read these, which we're gonna immunize. And then another issue is the time constraint. We don't want to fix, we want to fix the information before it's too late. We don't want it to spread out to the whole networks, okay? So a potential approach that we can take is why don't we put the good information to fix the misinformation, all right? So we have some kind of battle between good info and bad info. So information campaign. So let's take a look at how the good information gonna spread on the network. So the first thing is that good information gonna spread by the authorized user. That's some kind of obvious. And then the thing is by multiple direct activation. By that I mean if you have multiple friends that they believe in a tweet or a news, then you are likely to believe in that news as well. So there are a couple of campaign scenarios that we can take, when the good information comes first, then it's kind of immunization because you're aware of the good information already. So you're not believe in the bad info. And then when the misinformation comes first, then this is really bad because the good information has to correct the misinformation accordingly. For example, if we take a look back to the two examples, then a good information can be from an authorized user saying, hey, President Obama is still wealthy, something like that. And then what happens if they come they come at the same time? Then we need to decide which one to win over which one, right? So in this paper, we take the assumption that good information is gonna win over misinformation. Okay. So what do we study? In this paper, we study how the misinformation can be effectively contained. In particular, we ask the question, what is the type set of people in which dissemination would good information help to contain the ratio of misinformation to the particular desired ratio? For For example, in here we raise the 1 subtract beta, where beta is some kind of predefined parameter. And then we see what can we do when the source set of misinformation I is known or unknown, and when the time t is constrained or unconstrained. And we call this the beta IT node protector, where the beta is a desired ratio, I is a set of source nodes, and t is time constrained. And which node should we protect? For example, let's say this is a portion of the social network, whereas we have this kind of topology. And then say if we want to protect 50% of the nodes in the network with the good information, then we can choose these 4 guys. So we have a solution set of S of psi 4. But we can do even better by just choosing the guy in the middle, because he's kind of the big boss controlling, has a high influence with the other 3. Okay? So this is a good solution. This is an even better solution. Okay? And then we analyze a grading algorithm for this particular problem and see how good it is. And we discover that it has a linear additive error. And this shows an experimentally better law about the optimal solution for this particular problem. And then the next thing we're going to take a look at is the effect of the community structure. And why is that? We're going to explain it later on. But what does it help in here? It helps us to design a more intuitive and faster methods for this particular problem. And the result of that algorithm is competitively in comparison with the optimal solution and the greedy algorithm. Okay, so let's first step back and take a look at the graph model. In this problem, we're going to formulate an online social network as a directed graph where nodes are user and edges stand for the connection or relationship between users. And then a status of the user can be either active or inactive, where active means he exposed with the information, and inactive means he doesn't know about the information. And an active user can further propagate the information, or in other words, further influence the other nodes, other neighbors. For example, this is a snapshot of the network where you have 2 active users, and the rest are inactive, so they are not aware of the information. And in the next snapshot, the active user can spread out the news, so you have more active users out there, and these 3 guys, they still don't know about the information. So that's how the information spread. And the diffusion model, so we have the 2 diffusion model, and the independence cascade model, we already heard about, so I'm going to skip that. Just recap, you have a single chance to influence the other guys, and if that guy B is influenced, then he's going to further spread out the news. And the linear threshold, what does it say? It says that you need to have enough people to influence you, or in other words, you need to have enough probability strain in order to influence you, given that you have a certain threshold. For example, B has a threshold 0.5. So if he has more than 0.5 activation from his neighbors, then he's going to be activated. And then he's going to further prop out the activation probability. Well, in fact, people show that these 2 models are somehow the same. Somehow related to each other, and they can be regarded as one. And then dissemination model. So how do we inject people with good information, and how did that work? So in order to offer a fair game between the good information and the bad information, then we take the propagation of good information is exactly the same as the bad one. Well, in reality, we believe that the good information can propagate faster because from authorized personnel. And people tend to believe it more than that. And the assumption that we discussed is just recently that we take the assumption that good information wins over the bad information. This is a typical scenario in the real life. So with all that in mind, we formulate the problem that we're looking at is that in the presence of misinformation spreading on the network, so we know it's there, we just don't know who is injected with bad information, okay? Because we have a very large network. And then the question we ask is find the smallest set S of nodes who injected with good information expectedly achieve a desired decontamination ratio beta after T time step. And then you have for realization of this problem where the source set I and T and time T are unknown, known, or unconstrained or constrained. For example, and then it's not surprisingly that all of these beta versions are NP-hard, which means you're not supposed, or you're not, it's hard to find an optimal solution in a timely manner. Okay, so we already heard about the influence maximization. So what's the problem, what's the difference between our problem and that problem? So in an overall view, our problem is the reverse of that problem, or in other words, we take a look at the problem in the other way around. So where we don't have the K-node budgets, but instead we have the desired ratio beta, and we have a campaign of good and bad information. And then the two side effects, we have the constraint time T, and we have the knowledge of the source set I. Okay, so because our goal is to analyze how the greedy algorithm works, so we're going to take a look at how the result of this one is going to tell us about the optimal solution. So we take we analyze the greedy hill climbing algorithm. This is a fairly classical algorithm, in which step you add the node having the maximum gain into your current solution until you get what you want. I mean, until the influence of the current solution is big enough, okay? And that's called hill climbing because every step you walk to the best one that you can have. So this greedy algorithm offers a 1 subtract 1 over E approximation factor for the influence maximization problem. That's the well-known result. But what does it help in our problem? Okay, because these two problems can take the same approach, then what's the difference? Okay, so our analysis show that if we do like that, then the solution that we have has an additive error in terms of the optimal solution. That means we have this optimal solution plus the extra in terms of the number of desired nodes. So where E is the natural number 2.72 and delta is the smallest number of person you can influence in each route, okay? So what does it say? It says that if we have a bigger number of person we need to protect, then we have to choose more people into the solution and vice versa. And then one more thing is that greedy solution selects less than 36% of the extra node intuitively. If we just simply select beta n number of nodes from the network, then the solution is solved, okay? But then we show that we can do it even better. And if at every route we can choose this theta is to be big, say 4 or 5, then this 36% will be divided by 4 or 5. So we even get a better solution than that. And then this one gives us a better observation on the lower bound of the optimal solution in comparison with another known result for this one. That means this one is less than 1 plus log n, log beta n divided epsilon times the solution. So these two are going to give us the overview on the side of the optimal solution. But we will see which one is better. And then the approachability, that means we analyze for this particular, when we know the source set I and the time t is constrained, then how hard the problem is going to be. We show that we don't expect to have a good algorithm that can approximate this problem into the log n approximation ratio. And this is shown by a reduction from a set cover problem. And what does this actually say is that if this is this optimal solution for the problem, and this is C times log n, then you don't expect to have an algorithm that always returns a solution within this interval. And it also implies the non-existence of any logarithmic algorithm approximation factor for this kind of particular problem. So again, if we apply the greedy algorithm in here, what do we get? If time t is constrained, then we're going to look around for t-hop neighbor of a node. And if I is known, then what do? We look around for t-hop neighbor of the subset I. And then we apply the greedy algorithm on the restricted graph GI. And we get the same but slightly better ratio. Why? Because we exclude the number of nodes that's not going to be infected by the bad information because we have the time constraint T already. Okay, so we take a look at the experiment, and we do it into every WebSci network with 15 and 63,000 of nodes and 1.6 million of links. This is a fraction of Facebook network on the New Orleans region. And we compare with the other methods, the random, high degree, disguise, in pay rank. Okay, so this is the result, how it's going to look like. This is the result of the greedy algorithm. And it's give you the best ratio, the best result that we have. And if we take a look at the size of the optimal solution, then it would take the log n approximation factor, then it's going to tell you that the size of the optimal solution is somewhere around here. But our analysis show that the size of the optimal solution must be somewhere around the red line and the blue line, which show you a little bit more knowledge about the size of optimal solution, so you don't have the solution, the optimal solution, to be too small in comparison with what you have right here. Okay? And this is the same observation on two different kind of network where we have the beta I5 setting. Okay, so why do we need another approach on this? Because the greedy algorithm is too slow to be executed, and it's not ideal for larger network. So why do we take a look at the community structure of the network? Because this is a common property of online social network, and it's displayed the natural structure of the network. And this shows how people interact with each other, how people form a group, and the tendency between groups. And then, again, the method is quicker if you apply it in each community. Okay, so network communities is expected to be group of nodes where you have a dense connection inside and less connection between groups. So this is a snapshot of network community. So what do we infer? That we have a strong influence in each community, okay? And we have less influence across community. And this is perfect for our setting in finding the people with a stronger influence. And the community structure detection is the detecting of this spatial structure of the network. So a social-based method, what do we do? First, we find a network community structure by using the Plunder method. Why? Because this is fast and with high reality. This is thoroughly verified in the literature. And then we apply the greedy algorithm in each community. And what do we get? We get it's faster because the size of the community is smaller in terms of the home network. And then because the two observations that we already made. And then if you take a look at this, the red line is going to be the result of the community structure approach, and the green line is still the result of the, of the greedy algorithm. And if you take a look at the time, it's relatively faster. I mean, if not to say a lot, right? In these two average size network, it show you like a lot better in execution time. So in summary, what do we get? We get the greedy algorithm is good. It gives us approximation ratio and boundary whatsoever, and it returns the best solution so far. And then, but it's too slow and not ideal for big network. And then it gives us a new, we give a new point of view into the size of the optimal solution. It cannot be too small in comparison with the greedy solution. And then we said we experimentally verify that community structure is helpful. It helps you to explore the structure of the network and expedite the execution of the algorithm with good result. And just an acknowledgement of the funding agency and Dr. Wei Chen for providing the code of the algorithm. And here's a picture credit that I use. Okay. Thank you.